So we are talking about moments because we are talking about we are going to talk about bodies already. Up to this point, we have been talking about particles. And particles is just a point, as we saw in the previous last time, where the dimensions don't matter. Because for a particle, the rotation doesn't have a meaning, but for bodies, rotation have a meaning. The rotation of a body has meaning, but the rotation of a particle doesn't have a meaning. And in order to do rotation, we saw that we need a force and a distance. Only if I have a force applied at a certain distance from a point where the body can rotate, then there is rotation. You have a force and you have to have distance. That distance is called lever arm. And so we have to have a point about which there will be rotation. We have to have a force and we have to have distance. So remember that the distance has to be at 90 degrees from the line of action of the force. Very important concept. If you don't have the distance at 90 degrees from the force, then you have to find it. Because suppose you have this, you have point A, point B, let's say point B is the point of application of the force, and you have the distance in this direction. That is not 90 degrees. So this D doesn't work. So you have to find the distance at 90 degrees. So somehow you have to find this distance here. This distance is the one that could work at 90 degrees. If you cannot get the distance at 90 degrees, then you can eventually, you might be able to find the components of the force. Let's say you have this distance here. And this is the point of application of the force B. And this is the force here. So remember what you do here. You can take the components of the force. Let's say we can get here a component that is perpendicular to that line D, and the other that is parallel to that line D. So with these components, let's say call this Fn and this F parallel, and this is point B. Then here you can calculate the moment. The moment of F with respect to A will be just Fn times D. And you can say also that here, in order to be strict about it, then you can say that is plus FP times 0. Remember why that's 0, right? That 0 is because the force P, the point of application of force P and P, the line of action of force P, it goes aligned with the distance D. So it passes through point A. So the distance from point A to the line of action of FP is 0. So this moment is 0. So that's why this moment is just the normal force multiplied by D, because this angle is 90 degrees. Okay, I believe you should have that very clear from previous lecture and from previous examples, and you probably, I hope you guys went over the exercise that I recommended for you to do. And we are going to continue talking about moments. So the first thing that I'm going to do here is to talk about how we can move forces around, because now that we are not talking about a point anymore, Because when you are talking about a point, all the forces go through to the point. There is not much to do about it. But now we are going to start talking about a rigid body, a complete body. The forces can go in different locations, in different places, and we might be able to need to move around the forces in order to facilitate the calculations. So let's see what forces we can move and how we can move them. Let me do a drawing here. Let's see, we have this figure here. Let's say we have something like this. If this is a rigid body, and you have, let's say you have a force F applied here. Let's call it F1 here. And you have another force F2 applied here. And this is the line of action of the force. These two forces go through the same line of action. If this is a rigid body, then the summation of forces in the X, let's say this is the X axis, in the X direction here will be equal to F1 plus F2. Well, F2 will be in the other direction, will be minus F2. And if this is in equilibrium, then this should be equal to 0, the F1 equals F2. In this case of a rigid body here. If I move these forces through the line of action, let me copy this here. And let's say that we move force 1, if we move force 1 and we put force 1 here, force 1, and we move force 2 here also through the line of action here, force 2, force 2. The situation keeps being exactly the same. If you do here summation of forces in the X direction, you still have F1 minus F2 equal to 0, so F1 equals F2. Nothing has changed. We can move the forces along the line of action and nothing happens. This is only if we have rigid bodies. If we don't have rigid bodies, let me see if I can copy this again. Okay, good. If we have a deformable body, then let's say we have the force 1 here again, and the force 2 here again, force 2. If this is a deformable body, then this will go something like this. Because of the action of those forces, right? And this eventually will make some cracks over here, probably because of the tension and stress there. This is a concrete frame. That's what will happen with this deformable body. If you move the forces around, let's say that let's do another figure here. If we move the forces along the line of action, and now we have the force 2 here, the force 2 here, and the force 1 here. Now the situation is going to be very different. Now this is going to do something like this probably. And now it's going to have some cracks around here, right? So if the body is deformable, then in the first case, we'll have to do reinforcement over here in this section in order to avoid the cracks. And here is going to have the reinforcement of the lower part in order to remove those cracks. So it's completely different situation by applying the same motion of the forces through the line of action. So for the deformable bodies, we have to be careful how we move the forces, even if it is along the line of action. But this is not a problem in our class here. We are working with rigid bodies, so we can do this. We can move the forces along the line of action, no problem. It's what I should call a sliding sliding forces. Our forces can slide, sliding forces. We have sliding forces while we work in this class with rigid bodies. We are only interested in the equilibrium and not the deformability of the bodies. We can have the forces to move along the line of action. Forces can move, how can I say that? You can move the forces, you can move forces along their line of action, their line of action, and no problem, no problem. So wherever you have a force, you have force here. If you don't like it there because for some reason you need it somewhere else, well, you can move it along the line of action and you can put it in another place and okay. As long as it is along the line of action, you can move it, not a problem. Now, what happened? Let's put here another example. Let's say that you have a body like this, because now you're gonna need to move forces around in order to do your calculation. Let's say that you have the force P over here, but in this location, the dimensions are not easy to see or whatever, then you might need to move the force and put it in here, P. So P can go from here to here, okay, no problem. You can move it along the line of action, no problem. Let's say that here you have this dimension or whatever, or you know these dimensions over here very well. So for some reason you rather have the force located in here instead of here, you can do it, not a problem. Now what happened if we want to move the forces outside of the line of action? Let's say that for some reason you want to move the force here in this new location. So let's see what happens. That is not as easy. You cannot move forces out of the line of action as easy. So what happened? So we need to talk about moments now. Let's put the same this figure here. Let's put it a little easier. Let's see that you have a force here, F. This is the line of action of the force. If for some reason you need to move that force over here, let's say this was here on a point A, and now you need to put it on point B. You want to move the force from A to B, and there is a distance D here, D. So you have to be careful in order to do that motion, because what happened? The force F, it produces some kind of effect of motion to the right? And with respect to point B, it also produces some kind of rotation. You can feel like there is some sort of rotation here due to the force F with respect to point B. So there is actually a moment here on point B produced by force F. So if you want to move the force F to point B, you can move it. Right? But you have to also, you have to pay a price. You have to put the moment that the force was applying on point B when the force was in the previous location. So let me, maybe it's better if I make another graph here next. If I have this situation on the left, if now I have this situation on the left is the force right here. If I want to put the force here, now I have to include a moment that the force F was producing with respect to point B. and that moment was F times D, and this will be force A. So these two systems are equivalent. I can work with this system on the left, or I can work with this system on the right. Those two systems are equivalent. So if you, for some reason, you need to move the force F to a different location, so you have to be careful, because the force F, it was producing a moment with respect to the new location. So when you remove the force from point A, that moment will not be applied over point B anymore, because you remove the force from there. Now you put it here. So here there is no moment. This force is not producing moment with respect to point B. So you have to apply the moment. Additionally, to moving the force F to point B, you have to apply this moment, and the magnitude of that moment has to be equal to the moment that the force F was applied on point B when it was in the original position. Okay, so be careful with that. We have to deal with that from now on, because we're going, as I said, we're going to move forces around, and we're going to do some examples. Calculate, if you have a system of forces, calculate a different system of forces equivalent to the first one, but in a different position. You have to pay that price. You have to apply an extra moment every time you move a force. I'm talking about this concept about moving a force out of the line of action. I am moving the force out of the line of action. If I move the force out of the line of action, I cannot just move it. When I move it, I have to pay a price. I have to apply a moment because of the motion outside of the line of action. The force, it was applying a moment with respect to the new position. So when I move the force to the new position, I have to apply artificially, let's say it's artificially, I have to apply a moment to compensate for the fact that the force in the new position is not applying that moment anymore. So in order to have the same conditions, I have to have the force in the new position plus the moment that it was previously applied due to the previous position of the force. Okay, and the moment is equal to the force times the distance to the new position. Let's do a first example with numbers. Actually, well, let's put some numbers to this guy here. So let's say I have this force F that has a value of 20 newtons. Let's put it here, 20 newtons. And let's say that each one of these squares is 1 millimeter. 1, 2, 3, 4, 5, 6. This distance is 6 millimeters. And for some reason, I want to move that force from that location A to this location B. So now the force is gonna be here. F is gonna be here, 20 newtons. So if I am going to move that force from location A to location B, here, this force produced with respect to B a moment that is equal to the moment of force with respect to B in the original position is equal to F times D is equal to 20 newtons times 6 millimeters, so equals 120 newtons millimeters. So if I am going to move now the force F to this new location here, in order to keep this effect of this moment that it was applied here on point B, I have to apply the moment here of 120 newtons millimeters. All right. So again, this situation here is equivalent to this situation here. And if you need to do calculations on this, you can use this diagram here, or you can use this diagram here. Both of them are exactly equivalent. So you can do that trick. Probably you have some kind of condition due to the new position of point B, that you rather have the force at point B than at point A. Well, you move the force to point B, but you have to apply the moment. Okay? All right, let's leave it like that for now. Now let's talk about couples. Couples. We are not talking about two people decided to live together for good. No, we are talking about couples in statics here. A couple is two forces, but not just two forces. A couple, to be a couple, have to be two forces. They have to be parallel, and they have to be in opposite direction. That's a couple. Oh, one more condition. Two forces. Let's put it here. Two forces of same magnitude or equal magnitude. Equal magnitude. Two forces of equal magnitude. Parallel and in opposite directions. So if I have a force like this, and this is F1, and a force like this, and this is F2, you see them parallel right there. They go in opposite directions, right? You have here opposite directions. If F1 equal F2 in magnitude, as a vector, I will have to do something like this. F1 equals to minus F2. If I do this like in the Cartesian coordinates, F1 will be F1I. F2 will be F2 minus I. And let's say we say F1 equals F2 equals F. Then we can say here Fi equals minus Fi. So those are a couple. Here you can see the whole thing. That's a couple. And well, they will be separated by a certain distance. If they are not separated, they are in the same line. So it's basically zero. You put two forces of same magnitude in parallel and in the same line of action, you are doing nothing. You have one force in one direction, another in the opposite direction. You have one force here, another force here. So you basically have a big zero. There is nothing there. Two forces that balance each other completely. That will be. So in order to have a couple that really does something, you have to have some distance here. Let's call D. All right. That is a couple. A couple doesn't produce actual translation effect, doesn't push or pull, because the forces balance each other because they are in the same line or in the same direction but opposite sense. So they kind of balance each other, but due to the distance, they produce rotation. There will be a sense of rotation like this, right? You can see it by the direction of the arrows. I hope that you guys can see that there is some sense of rotation. The sense of rotation, we can find it by calculating the moments with respect to any point in the space. Let's do it here, like on a figure. Let me draw a figure here. Let's say something like this again. Let's say that I have a couple applied to this. I have a force here, F1 equals to 10 newtons. And I have another force here. Let's put it here. F2. If we want this to be a couple, this has to be also 10 newtons. They have to be in the same direction. They have to be in the opposite sense and same magnitude. So let's calculate the moments of that couple with respect to point A here. Let's say that each one of these squares is 1 millimeters. So if I want to calculate the summation of moments or the total moments that these forces are applying to point A, if we say something like this, summation of moments of all these forces with respect to point A, and let's say that we're going to do positive clockwise, then that summation will be equal to force F1 doesn't produce moment with respect to point A, right? Because the line of action of that force goes through the point. So the distance from the point to the line of action is 0. So we have a F1 times 0. And the force F2 goes in this direction. So with respect to A, produce rotation in this direction. So will be clockwise. So that will be a positive rotation. That will be F2 times the distance that if every little square is 1 millimeter, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 millimeters. So will be equal to 10 newtons times 9 millimeters equals to 90 Newton millimeter. All right. That is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this distance is 9 millimeters. All right. Now let's calculate the moment of that same force with respect to that same couple with respect to point B here. Summation of moments with respect to B, and let's say positive in the same clockwise direction. That will be F1 times, so now the distance from F1 to point B, let's put it point, let's say that point B is exactly here, right? And this is point B. So this distance is 1, 2, 3, 4, 5, 6, 7. So this is 7. And from this is gonna be 2. Okay, so we have moment of the force 1 with respect to B will be 10 newtons, or the force 1 times 7 millimeters, plus force 2 times 2 millimeters, right? The distance from force 2 to point B, 2 millimeters. So it'll be equal to F1 is 10 newtons times 7 millimeters plus 10 newtons times 2 millimeters. So this is equal to 70 plus 20, 90 newtons millimeters. So you see that the couple produce the same moment with respect to any point that you want, any point. Let me do a more okay, a more general case. Let's calculate the moment of that couple with respect to a point located over here, point C, at a distance x, any distance x, so it will be any point in the universe. X is any value. So the summation of moments with respect to point X, and let's do positive clockwise, will be equal to what? The fourth one?
F1, 9 plus X.
Right. The fourth one multiplied by 9 plus X. In what direction? So first one goes this direction with respect to point C is this direction, right? So it will be clockwise or positive. Now, force 2 times X, right?
Yep.
But that goes in the opposite direction because this one goes like this. So it produces rotation in this direction with respect to.
Yeah, it's minus, you're right.
Minus here. So that will be F1 10 times 9 plus X minus F2 10 times X. So it will be equal to 90 plus 10X minus 10X. So this goes with this equals 90 Newton meter. See? So you see how the moment is still the same with respect to point A, 90, with respect to point B, 90, with respect to any point at any distance, X is still 90. So the couples produce moment no matter what you put in. So couples, you can move around very freely. So it's the same if you put the couple here or if the couple is far away, still the moment with respect to any point is going to be the same amount. So it doesn't matter when you have the couple, it has the same value. So you can replace. Does
mean FD is constant then?
The moment doesn't change. So you can replace this. Let me put it right here. A moment like this. It's a song by Kelly Clarkson, no? A moment like this. Do you guys remember that? Or you guys are too young? You remember when Kelly Clarkson won the American Idol? You guys remember or you don't remember? And the day she won, she sang that song, so emotional. A moment like this. Let me remove all this.
Hey, Professor, I have a quick question for you.
Yes, let me finish. 90 Newton. Yeah, one second.
I'll let you.
Just 1 second. Look, because this is kind of amazing here. So you can have either this set here with your couple apply on those points, or this here with the couple apply in any point. 90 Newton meter apply anywhere is equivalent to the two forces in those locations that I showed at the beginning. All right. Yeah. What is the question?
It's a pretty minor one. The textbook treats the clockwise moment as negative and the counterclockwise as positive. Does it matter which one of those systems I use as long as I'm consistent with it?
Yeah, very interesting question. In general, we consider X positive going to the right, Y positive going to up, right? And this direction we always consider positive like that, right? That, right? We can use that, not a problem. We can use that. But in a specific calculation, you can set up any convention of signs that you want in order to find an answer. And then when you get the answer and you get the sign according to your own system of signs, then you know the direction of your moment. And then you can say, okay, it's clockwise or it's counterclockwise. For example, here I said, clockwise is positive. So when I do my calculations, I found that 90 was positive, so this is clockwise, right? Same here. So at the end of my calculations, I look at the sign and then I look at my own convention. And according to my own convention, I can write here clockwise or counterclockwise. The important thing is to know in what direction you have the rotation. That's the important thing. We could say for now, okay, every time we talk about positive is counterclockwise. We can do that. Or if we don't say anything, we should say, okay, if you don't say anything, I am assuming that you are using the convention that everybody uses, which is counterclockwise positive. I personally, I use the convention that is more convenient for me in a specific equation. And then after I finish the equation and I find my result, I put the label clockwise, counterclockwise.
That makes sense.
You have to be the master of the universe. You don't have to let the universe govern you. You have to be the one that governs the universe. So you set your own rules as soon as the final answer is correct and you express your final answer in a way that everybody understands. And everybody understands clockwise and counterclockwise. That has meaning for everybody. So let's do a couple of examples here. All right, so, well, basically the figure shows what it is. Let's see if there is anything else. Two parallel 60 Newton force are applied to a lever as shown. Determine the moment of the couple formed by the two forces. Okay, we're going to calculate the moment produced by this couple. When you have a couple, that couple produces a moment. And the moment is equal to the magnitude of the forces multiplied by the distance. I don't know if I said that specifically somewhere here, couples. I should say it here. Sorry. If you remember this, the moment the couple produce is equal to, oh my goodness, sorry. That's a very big missing. Moment is equal to force times distance. That's the magnitude of the moment produced by a couple. The magnitude of the forces, which is the same for both, so any value, the magnitude of either one of the forces multiplied by the distance between them is the moment produced by the couple. And the distance you have to measure again at 90 degrees, right? So let's go back here. If you have this couple here on this example here, you have a moment, a force that goes like that, a force that goes like this. The force is 60. This one is also 60. If we can find the distance here at 90 degrees, then the moment is equal to 60 times d. That's the magnitude of the moment produced by the couple. And most probably one of the questions is calculate the moment by calculating, by using the distance between the forces. I'm pretty sure that's one of them. Let's see. Determine the moment of the couple formed by these two forces. A, by resolving each force into horizontal and vertical components and adding the moments of the two resultant couples. B, by using the perpendicular distance between the two forces. C, by summing the moments of the two forces about point A. Okay, very nice. So we will practice everything here. So let's go first. A, by resolving each force into its horizontal and vertical component. Then let's do it here. So we have this bar. Maybe I use my little ruler, my handy ruler. I love my handy ruler. So I have this line here. This line, and I have the forces. I have this force here. Before I forget, let's put it here very big. Before I forget, guys, I always talk about the sketch, the diagram. The diagram has to be nice, big, and a size to put all the dimensions, the angles. But above all, there has to be a diagram in our problems here and in engineering in general. If you don't have a diagram, you don't know what you're doing. And if you And if you start to set an equation, summation of forces in the x direction equal to 0. If there is no diagram, you don't know what forces you're talking about. I am saying this because I received quite a few homework where there is no diagram. And I always say missing diagram, and I take up some points. So please, very, very important. In all these problems, there has to be always a diagram. Always, always, always. Never miss the diagram. Okay, so we have here 55 degrees. And then we have here 20 degrees. This is 20 degrees. Now this guy is telling us first, by resolving each force into horizontal and vertical components. So we have to do horizontal and vertical components. So we put here the horizontal component here. Let's put the horizontal component here. And the vertical components, this component right here, and this component right here. Okay, so we'll have, maybe I should remove this line here, it's kind of confusing. We should put some names here because it's gonna be, let's call this one F1 and this one F2. So this one will be F1X and this F1Y. This one will be F2Y, so F2X. So, determine the moment of the couple formed by the two forces by resolving each force into horizontal and vertical components and adding the moments of the two resulting couples. So now we have two couples here, right? We have one couple, which is this F1X and this F2X. And we have another couple here, which is F1Y and here F2Y. So this, we have to find this distance here. Let's call it dy because it's for the y components. It doesn't look very logic, but and let's call this one dx because it's the one that separates the x components. So can we find this distance? Can we have these components? So we have all the angles that we need. This angle is 20 degrees. This angle down here is 55 degrees. So dx will be equal to, this distance here is 360 millimeters. 360. So dx is equal to 360 cosine sine 55. So that will be 294.9, 189. dy will be equals to 360 times cosine of 55, 206.49, 206.49, 206.49. And now we need to find F1X and F1Y. So F1X is equals to F1, the forces are 60, both of them. So this is 60 cosine 20, 56, 382. And Fy will be here 60 sine 20, 20, 52, 1, 20, 52, 1. So we're ready to make the first calculation. The couple produced by the horizontal forces makes a rotation like this, right? I'm gonna call it positive. I'm I'm gonna call it positive. I'm gonna say this is positive for me. Positive for me is clockwise. Doesn't matter. Or we can use positive counterclockwise, so we use what everybody uses. This is the same. Now, this one produce rotation on this direction, right? So let's do the calculation. X components, or let's call it X couple. X couple. Let's call it mom X equals to the force 56.382 times 294.89 equals to 1.6. I'm going to divide by 1,000 so I get this in newtons meters, not newtons millimeters. 16.626626 newtons meters. And is positive according to my convention here. Now, moment Y couple My equals to the value of the force 20.521 times the distance 206.49. So it's gonna be 20.521 times 206.49, 4,237.4 newtons meters. But this one is counterclockwise, so this one is negative. I have to put a negative here and here. So if I want the total moment produced by that couple, it will be the summation of these two, will be 16 minus 4. 16.626 minus 4.2374, it will be 12.389 newtons meters. Positive. If it's positive, it's clockwise, according to my sign convention. If I get positive, it is clockwise. So this is the one that is important. It's clockwise. All right. So this is the moment of the couple. I can remove the sign here and just leave the clockwise. That's the moment of the couple. So in this case, we calculated the moment produced by those two forces as we get the components of each force in vertical and horizontal component. In that way, we created two couples. One couple with horizontal forces, another couple with vertical forces, and we calculate both moments by multiplying force times distance, and we get the summation of those two, and that's how we got the total moment. Let's do the second by using the perpendicular distance between the two forces. Okay, so now let's do the same calculation, but using the distance between the two forces. That distance will be this distance right here, D. And what is that distance? That distance D, let's put it over here, is gonna be 360 times sine of this angle. Let's see if we can find this angle. Let's make a little diagram here. This is 20 degrees. This is 55 degrees. So this is 35, right? 35 degrees, because all this is 55. 55 minus 20. So now the vertical line between those two forces is gonna be this distance here, D. equals to 360 sine 35. 360 sine 35. 206.5. 206.49. So the moment, we can do it very quickly. The moment will be the magnitude 60 times 206.49 equals to 206 times 60, 12,389. 12.389. I was sweating here. This is not gonna give me the right value. This is not gonna give me the right value. Look, yeah. Same thing, right? Now the next one. I'm gonna leave the next one for you. By summing the moments of the two forces about point A. I should leave that one for you guys. Remember that I said that a couple produces a moment. A couple of forces produces a moment, and that moment is a free vector. You can put it anywhere because remember that this moment is the same value no matter with respect to what point you calculate the moment. So if you calculate the moment of those two forces with respect to point A, you have to find the same value, 12.4. You have to find the same value, right? And you guys know how to calculate moments. That's what you did last class, and you were doing practice with all the examples I did and the example that you also ran on your own. So at this moment, you have to be able to calculate the moment of a force with respect to a point. If the force is a little twisted, crooked, and misaligned, you have to be able to find with some angles and some dimensions, you should be able to find the way to calculate that moment. Either by components or directly by force times distance. So now we need to calculate the moment of these forces F1 and F2 with respect to point A. Everyone finds the best way that you want. For example, let's see, we can do it directly force times distance. If I have this, so I need this distance. Let's call it D1. And let's call this D1. And let's call this D2. If I can find that distance, D1 and D2, I can calculate the moment as F1 times D1, and that will go in this direction, right? And the other will be F2 times D2, and that will go this direction. Does everybody see that? Anybody doesn't see that? So the moment will be the summation of those two moments. Let me put it right here. The moment will be F1, which is 60, times D1. D1 is equal to the total distance. If you guys remember the problem, the other distance was 520. I can barely see it's 520. Let's say it's 520. Let's say 520 because I don't see very clearly. So this is 520. So the total distance here is 520 plus 360 is 880. 880. So D1 is 880 times sine of this angle here. Anybody can tell me what is this angle here? That angle will be 55. This is 55. So this will be 55 minus 20. So 35. And the other will be, F2 will be, let's call it this, N1, N2, N1, N1 equals, let's do this one. 60 times 80 times sin 35, 32, in this direction. And the other M2 will be F2 times D2. F2 is 60, D2 is this one here, which is 520 sine of 35. 520 sine of 35 equals 17,896. 896. In what direction? Clockwise or counterclockwise? This force here goes like this around point A. So this is, if this one is in this direction, the one F1. So I didn't put any convention. So if we didn't do any convention, let's do the one that everybody uses. Counterclockwise is positive. So then we will have positive for this one, counterclockwise here, and negative for this one. So this is negative. If I take the summation, will be this 17,895, 12,389. Negative 12.389 newtons meters. Negative, if we are using the convention that everybody uses, so negative is clockwise. So this is clockwise. So this is our answer. Here the sign, I don't care about the sign anymore because I put the label clockwise. So let's see if we got the same thing. Yay! Right.